There is a specific moment in the re-entry of a crewed spacecraft when there is nothing left to do. The engines are off. The parachutes haven't deployed yet. The crew is strapped in, weightless, and outside the capsule, the air is compressing so violently that it becomes a plasma, a state of matter hotter than the surface of the sun. The only thing standing between the crew and that plasma is a disk of material bolted to the bottom of the capsule. If that material fails, the crew does not survive. There is no abort option. There is no contingency procedure. There is no version of this story that ends with everyone going home. That disk of material is the heat shield. In December 2022, the Orion spacecraft returned from its first uncrewed test flight around the moon. It hit the atmosphere at over 39,000 kilometers per hour. The heat shield did its job, the capsule splashed down in the Pacific Ocean, and NASA declared the mission a success. And then the engineers looked more closely at the heat shield. What they found is the subject of this video, because what they found was not what they expected. And what they found is the reason that the first crewed Artemis mission, Artemis II, which will carry 4 human beings farther from Earth than any person has gone since 1972, has been sitting on the ground for months longer than planned, while a team of engineers and program managers works through a problem that, if it is not fully understood before the crew launches, could kill everyone aboard during the most dangerous 11 minutes of the mission. This is not a story about bureaucratic caution. This is not a story about NASA being overly conservative. This is a story about a spacecraft that behaved in a way its engineers did not predict. During the phase of the mission that has no margin for error, in a way that reveals a gap between the models used to design it and the physical reality of what actually happens when it re-enters the atmosphere. The heat shield cracked. Not completely, not catastrophically, but in a way that was not supposed to happen, in a way that was not in the models, in a way that under different conditions, higher velocity, different trajectory, a crewed vehicle with a heavier return load might have been worse. And the crew of Artemis II, Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen, is going to fly on this spacecraft. They are going to travel to the moon on it, and they are going to come back in it through the same atmosphere, at the same speed, with the same heat shield that already showed the world something it was not supposed to show. Let's talk about what happened. Chapter 1. The mission that was supposed to be routine. The Artemis. One mission launched on November 16, 2022. After years of delays, cost overruns, scrubbed launch attempts, a pandemic, and the accumulated frustration of a program that had been promising a moon mission for a decade, the Space Launch System finally left the launch pad at Kennedy Space Center and performed exactly as planned. The rocket, the most powerful ever successfully flown, carried the uncrewed Orion spacecraft on a trajectory around the moon and back over the course of 25 days. The mission was designed to answer one core question: can this spacecraft survive the journey to the moon and return safely? Not with crew aboard, not yet. Artemis I was an uncrewed test flight, a shakedown cruise, the kind of mission that exists specifically to find problems before you put human lives on the line. Every major crewed spacecraft program in history has included uncrewed test flights, precisely because the only way to truly know how a spacecraft performs in the flight environment is to fly it there and find out. The Orion spacecraft performed well on the journey out to the Moon. It completed its powered flyby of the lunar surface. It entered the distant retrograde orbit, a large, stable orbit around the Moon that the mission was designed to maintain for several weeks. It fired its main engine to depart that orbit and begin the journey home. The onboard systems worked. The communications worked. The European Service Module, which provides the spacecraft's propulsion, power, and life support, performed without significant anomaly. The critical phase was re-entry. Re-entry is always the critical phase. It is the phase in which the spacecraft transitions from the vacuum of space, where there is nothing to interact with, to the dense lower atmosphere, where there is everything to interact with. At a velocity that compresses the air in front of the capsule into a plasma exceeding 2,760 degrees Celsius. The crew module is protected from this plasma by the heat shield, which is designed to ablate, to burn away progressively, absorbing the enormous thermal energy in the process and keeping the internal temperature of the spacecraft at survivable levels. The Artemis I re-entry was different from a normal ballistic re-entry in one specific and important way. Rather than plunging directly into the atmosphere on a single straight trajectory, the Orion spacecraft performed what engineers call a skip re-entry, a maneuver in which the capsule first dips into the upper atmosphere, generates lift aerodynamically, briefly skips back out into the thin upper edge of the atmosphere, and then makes a second, steeper, final plunge. The skip is not accidental. It is a deliberate design feature that allows the spacecraft to target a specific splashdown location with much greater precision than a direct ballistic entry would allow. A direct re-entry from lunar distance gives you a relatively small footprint of potential splashdown zones. The skip re-entry dramatically expands that footprint, allowing the spacecraft to target the recovery ship and the recovery teams wherever they are positioned. The skip re-entry also does something else. It changes the heating profile. In a single, ballistic re-entry, the heat shield faces a single, continuous pulse of aerothermal heating. In the skip re-entry, the heating comes in two phases. A first pulse during the initial atmospheric dip, then a reduction during the skip, then a second pulse during the final re-entry. The total integrated heat load may be similar, but the temporal pattern is different. And the temporal pattern of heating matters for how the heat shield material responds. The Orion capsule splashed down in the Pacific Ocean on December 11th, 2022. It was recovered by the USS Portland and its crew. The recovery looked exactly as planned. The capsule was intact. The parachutes had deployed correctly. The flotation devices worked. The external cameras had captured footage of the atmospheric entry that would later be analyzed in detail. Everything looked fine, until the engineers started examining the heat shield. Chapter 2: What They Found. The Unexpected Char. The heat shield on Orion is a disk of material called avcoat, applied to a fiberglass honeycomb substrate, covering the entire base of the crew module. Avcoat is an ablative material. It works by burning, or more precisely by controlled ablation, a process in which the surface of the material progressively erodes during re-entry, absorbing enormous thermal energy in the phase transition. As the outer surface heats up, it chars and then erodes away, and the charred material insulates the underlying fresh material, which in turn ablates. The ablation is designed to be progressive, controlled, and predictable. The thickness of the heat shield is calculated based on the expected ablation rate, and the heat shield is thick enough to provide the required protection with margin to spare. Avicoat is not new. It is the same basic material that protected the Apollo command modules during their re-entries from the Moon in the 1960s and 1970s. The Apollo heat shields were made of Avcoat applied as a foam in a honeycomb pattern, and they performed reliably through 11 crewed re-entries from lunar distance. So when the Orion program selected Avcoat for the Orion heat shield, there was an extensive heritage base to draw from. But the Orion Avcoat is not identical to the Apollo Avcoat. The manufacturing process has been updated. The application method has been refined. The substrate is different, and the re-entry conditions are different. The skip re-entry produces a thermal loading history that the Apollo heat shields never experienced. When engineers examined the Orion heat shield after Artemis I, they found what they described, in the careful language of technical reports, as unexpected material loss. More specifically, they found that in certain regions of the heat shield, the char layer, the burned insulating outer layer of ablated Avcoat, had not ablated smoothly and progressively as designed. Instead, it had cracked. The cracks had propagated through the char layer, and pieces of the charred material had ejected from the heat shield surface. The ejection of char pieces from the heat shield is not supposed to happen, or rather, it is not supposed to happen in the way it happened on Artemis I. Some material loss is expected and designed for. The ablation process naturally involves some material departure from the surface, but the char ejection observed on Artemis I was different in character from the designed ablation. The char layer was forming in a way that was mechanically compromised, cracking in patterns that the models did not predict, and then failing in a way that removed material in chunks rather than progressively eroding. The non-uniform distribution of the char ejection was also alarming. The damage was not uniformly distributed across the heat shield surface. Certain regions showed normal ablation behavior. Other regions showed the anomalous cracking and ejection. The pattern of damage was patchy, irregular, and, most significantly, not predicted by any of the ground testing or computational models that had been used to design and validate the heat shield. This last point is the one that should make anyone paying attention stop and think carefully. But before getting to what the failure of the models means for the program, it is worth making the physical reality of what was found more concrete. The Artemis I heat shield has a diameter of 5 meters, roughly the size of a large living room. When engineers inspected it after recovery, they were mapping a surface that had been exposed to temperatures hotter than the surface of the sun. The regions of normal ablation, where the Avcoat had progressively eroded as designed, showed a smooth, uniform char surface, blackened and slightly textured, consistent with the progressive ablation the models predicted. The regions of anomalous behavior were different. The char surface in those regions was disrupted, fragmented, with visible cracks running through the char layer. In some locations, the char had spalled off in pieces, leaving behind exposed subsurface avcoat that had experienced the thermal environment without the protection of the overlying char. The size of the ejected pieces, inferred from the size of the exposed areas and from fragments recovered from inside the protective cover that surrounded the heat shield during splashdown and recovery, ranged from small chips to pieces several centimeters across. Several centimeters across. In a heat shield context, that is not a trivial size. A piece of char several centimeters across that ejects from the surface during the second heating phase of the skip re-entry takes with it the thermal protection function of that area. The fresh avcoat underneath, now exposed, must absorb the heating load that the ejected char would have absorbed. On top of the heating load it was already going to absorb during normal ablation. The local ablation rate in that exposed area increases substantially. What engineers calculated after careful analysis of all the damaged locations and their corresponding positions in the thermal model was that the total effective reduction in heat shield margin, the reduction in the safety buffer against heat shield burn-through, was larger than any single region of damage suggested. The damage was distributed across the surface in a way that collectively consumed more margin than the program's pre-flight analyses had accounted for. Ground testing and computational models are the foundation of spacecraft design. Every system on a spacecraft is tested before it flies. In vacuum chambers, in thermal cycling facilities, in vibration test stands, in arc jet facilities that simulate the aerothermal environment of re-entry. The heat shield was tested. The avcoat material was tested. The specific thermal environment of the skip re-entry was analyzed and modeled. The models said the heat shield would perform in a specific way. The heat shield did not perform in that way. The deviation between the model prediction and the flight measurement is not a minor discrepancy. It is a qualitative difference. A failure mode that was not in the models at all, not a mode that was the models, but at a slightly different magnitude. When a spacecraft component fails in a mode that wasn't in the models, it means the models are incomplete. They are missing a physical mechanism. And when you are designing a heat shield, when the question is whether crew members live or die during re-entry, having an incomplete model is a serious problem. Chapter 3: The Physics of the Skip. Why the re-entry profile is the culprit. To understand why the heat shield failed in the way it did, and why the skip re-entry is the suspected culprit, you need to understand what happens to the avcoat material during re-entry at a physical level. When the Orion spacecraft hits the atmosphere at 39,000 kilometers per hour, the air in front of the heat shield cannot get out of the way fast enough. It compresses violently, and the compression converts kinetic energy into heat. The temperature of the compressed air at the stagnation point, the point directly in front of the heat shield where the compression is greatest, reaches approximately 2,760 degrees Celsius. This is hotter than the surface of most stars. It is hotter than the melting point of iron, steel, or titanium. The only reason the Orion capsule is not simply destroyed by this temperature is that the heat shield absorbs and dissipates the thermal energy before it can reach the capsule structure. The avcoat material begins to char at approximately 400 degrees Celsius. The char layer that forms is an excellent thermal insulator. It has very low thermal conductivity, which means that heat does not flow easily through it. Below the char layer, the fresh AV coat is protected from the worst of the heating, while the char layer slowly erodes from its outer surface. The char layer reaches temperatures of over 1,000 degrees Celsius on its outer surface, while keeping the underlying material at relatively moderate temperatures. This is the basic physics of ablative heat shields, and it works. The problem with the skip re-entry emerges when you trace what happens to the char layer through the two-phase heating. During the first atmospheric dip, the heat shield begins to heat up and the AV coat begins to char. The char layer forms on the outer surface, absorbing and dissipating thermal energy. At the end of the first atmospheric dip, as the spacecraft skips out of the atmosphere, the aerothermal heating drops significantly. The heat shield surface begins to cool. The char layer, which was at very high temperature during the first dip, begins to lose heat, partly radiating to the cold of space, partly conducting back into the underlying fresh AV coat. This cooling phase is critical. The char layer that formed during the first atmospheric dip is a mechanically different material from the original AV coat. It has experienced pyrolysis, the thermal decomposition of the organic components of the AV coat, and it has a different density, different thermal conductivity, and different mechanical properties from the original material. As it cools during the skip phase, it contracts thermally. The underlying AV coat also changes temperature, but at a different rate because of its different thermal mass and thermal conductivity. The differential thermal contraction between the char layer and the underlying fresh AV coat creates mechanical stress at the interface between them. A shear stress that tends to delaminate the char from the underlying material. If this stress exceeds the mechanical strength of the char cracks. If the cracks propagate fully through the char layer and reach the interface with the fresh AV coat, pieces of char can delaminate and eject from the heat shield surface. This is the leading hypothesis for what happened on Artemis I. The skip re-entry created a two-phase heating cycle that caused the char layer to form, cool slightly, and then be subjected to a second heating pulse. The cooling during the skip phase may have increased the brittleness of the char layer or altered its stress state in a way that made it more susceptible to cracking and ejection during the second heating phase. The result was the anomalous char ejection pattern that the post-flight inspection found. This hypothesis has been partially validated by updated computational models and by arc jet testing conducted after the Artemis I re-entry. The arc jet tests, which use a high-power plasma jet to simulate the aerothermal environment of re-entry, have been conducted with heating profiles that approximate the two-phase loading of the skip re-entry. And they have produced char behavior more consistent with the flight data than the original single-phase tests did. This is an important validation of the hypothesis, but it is not a complete resolution of the problem. The word partially matters here. The models have been updated and they now do a better job of explaining what was observed on Artemis I. But the updated models are not fully validated. They have not been flown. Their predictions about what will happen on Artemis II, with a crewed vehicle, potentially on a slightly different re-entry trajectory, at the same or slightly higher return velocity are predictions based on physics that was not in the original models, and that is being tested against a limited dataset of exactly one flight. One flight. The entire foundation for understanding this specific failure mode is a dataset of one re-entry, plus the results of ground-based arc jet tests that approximate but do not perfectly replicate the flight environment. The arc jet tests cannot fully replicate the real aerothermal environment of re-entry. The scale, the flow conditions, the exact temperature distribution, the exact chemistry of the plasma, and this limits how confident engineers can be in the predictions generated from updated models calibrated on those tests. Chapter 4: What within limits really means, and why. The language matters. When NASA first publicly acknowledged the heat shield anomaly, in February 2023, the agency used a specific phrase to characterize the situation. The heat shield had performed within acceptable limits. The investigation was ongoing. The team was working to understand the anomaly before the crewed mission flew. Within acceptable limits. This phrase is doing an enormous amount of work, and it is worth unpacking very carefully, because the difference between what it technically means and what a reasonable person might understand it to mean is significant. Within acceptable limits technically means that the heat shield provided sufficient thermal protection to keep the capsule intact through re-entry. The anomalous char ejection, whatever it was, did not result in a breach of the heat shield. If there had been crew aboard, the capsule would have survived. In that very specific binary sense, did the capsule survive or not? The heat shield performed within acceptable limits. But within acceptable limits does not mean that the heat shield performed as designed, that the heat shield behaved as the models predicted, that engineers understood why it behaved the way it did, that the failure mode observed was expected or planned for, that the same performance can be guaranteed on a crewed re-entry with the same or higher return velocity. It means only that this one time, the anomalous behavior was not catastrophic. The margin was sufficient. The char ejection happened in a way that did not expose the underlying structure. The spacecraft survived, but margins are precisely what you lose when you encounter a failure mode that wasn't in your models. When the models predict the heat shield will ablate in a specific way, and the heat shield does not ablate in that way, the margins you calculated are no longer trustworthy. You calculated margins against a failure mode you understood. You have now observed a different failure mode, one whose margins you did not calculate because you did not know it existed. The fact that it did not result in catastrophic failure on this flight does not tell you where the boundary of catastrophic failure is. The NASA Office of Inspector General understood this distinction very clearly. In its November 2023 report on the Artemis II readiness, the Inspector General Paul Martin wrote that the agency's characterization of the anomaly as within acceptable limits was technically accurate, but potentially misleading because it did not convey the more important fact that the anomaly represented a physical mechanism that was not in the models, whose full implications had not been characterized, and whose safety margins had not been established through analysis or test. The IG specifically noted that the framing of within limits, suggested a situation under control that was not, at the time of those communications, under control in any sense that fully informed decision-makers should find acceptable. The IG's report went further. It drew a historical parallel that NASA employees and observers of the space program recognize immediately: the pattern of the Challenger disaster and the Columbia disaster. In both cases, a technical anomaly was observed and documented. In both cases, engineers within the program raised concerns. In both cases, the anomaly was characterized by program leadership as within acceptable limits or as a known acceptable risk. In both cases, the concern was not adequately communicated to the decision-makers who needed it to make the call to fly or not fly. In both cases, the spacecraft was lost with all crew. The IG was not saying that Artemis II will fail the way Challenger and Columbia failed. That is not what the comparison means. The comparison is about a pattern of institutional behavior, specifically, the pattern of characterizing anomalies in ways that minimize their apparent severity in external communications, in ways that do not convey the full extent of the uncertainty to external stakeholders. Whether or not the Artemis II heat shield ultimately proves to be safe for the crewed mission, the institutional behavior observed in how the anomaly was communicated was a pattern that has preceded catastrophic failure before. And the IG was doing its job in pointing that out. This is not a comfortable thing to write about or to hear about. The people who work on the Artemis program are talented, dedicated engineers and program managers who are genuinely trying to get this right. The characterization of the anomaly as within limits was not a lie. It was a technically accurate statement that, in the context of how it would be interpreted by the non-technical audience it was addressed to, conveyed a false impression of the level of understanding and certainty the program actually had. There is a difference between lying and providing technically accurate but contextually misleading information, and in safety-critical programs, that difference matters. Chapter 5: The Investigation: 2 years of work on one problem. From the moment the heat shield anomaly was confirmed in early 2023, a dedicated team at NASA's Johnson Space Center, Kennedy Space Center, and the Avcoat manufacturing facilities at Textron Systems has been working on understanding it. The investigation has proceeded in parallel along 3 tracks: analytical, updated computational models, experimental, arc jet testing with 2-phase heating profiles, and material, physical examination of the Artemis I heat shield in detail to characterize the nature of the char damage. The physical examination of the heat shield itself has been one of the most important sources of information. The recovered crew module has been subjected to detailed inspection, with the heat shield being mapped region by region to characterize the distribution and severity of the anomalous char ejection. Samples of the heat shield material have been sectioned and examined under microscopy to characterize the microstructure of the char at different depths and in different regions, comparing the regions of anomalous behavior to the regions of normal behavior. This examination has produced important insights. The char ejection is not occurring uniformly across the heat shield. It is concentrated in specific regions that correspond, in the thermal models, to the areas of highest heating during the first atmospheric dip. The correlation between the high heating regions and the anomalous char behavior is consistent with the hypothesis that the two-phase heating is the mechanism. The regions that heated most intensively during the first dip formed the most heavily charred layers, which then experienced the greatest thermal stress during the cooling of the skip phase, and which were therefore most susceptible to cracking and ejection during the second heating phase. The material sectioning has also revealed something important about the nature of the crack formation. The cracks are not random. They have a preferred orientation that is consistent with the thermal stress field that the two-phase heating would produce. They run roughly parallel to the heat shield surface through the char layer at a depth that corresponds to the thermal gradient boundary. The location where the temperature gradient is steepest, and therefore where the differential thermal contraction between hot surface char and cooler subsurface material is greatest. This is exactly where the mechanical models, updated to include the two-phase heating dynamics, predict the stress concentration to be highest. The ArcJet testing program has been extensive. Teams at NASA's Ames Research Center, which operates the most capable aerothermal testing facilities in the world, have conducted hundreds of test runs on AVCoat coupons and on larger-scale heat shield segments, using a variety of heating profiles designed to approximate the two-phase thermal loading of the Artemis I skip reentry. The results have been broadly consistent with the updated models. Two-phase heating produces more anomalous char behavior than single-phase heating, and the behavior produced in the tests is more similar to the Artemis I flight data than the original single-phase tests were. But the ArcJet tests have also revealed something that complicates the picture. The severity of the char ejection in the tests is sensitive to specific details of the heating profile. The exact magnitude of the first heating pulse, the exact duration and degree of cooling during the skip, the exact time history of the second heating pulse. Small variations in these parameters produce meaningfully different chart behavior. This sensitivity means that the exact trajectory and heating profile of the re-entry matters significantly for how the heat shield performs. For Artemis II, the re-entry trajectory has been modified in response to the heat shield investigation. Specifically, the program is evaluating adjustments to the skip geometry, the entry angle, the altitude of the skip, and the timing of the final re-entry maneuver that are intended to reduce the peak heating during the first atmospheric dip, reduce the temperature differential in the char layer during the skip phase, and therefore reduce the thermal stress that is believed to drive the anomalous char cracking. The specific trajectory modifications are still under development, and their effectiveness has not been demonstrated in flight. The Orion crew module for Artemis II, designated Orion 004, has a heat shield that incorporates manufacturing improvements relative to the Artemis I heat shield. The manufacturing improvements focus on the AVCoat material's microstructure, specifically on reducing the void content and improving the uniformity of the char formation properties. The hypothesis is that more uniform AVCoat microstructure will produce a more mechanically robust char layer that is less susceptible to cracking under the thermal stress of the two-phase heating. Laboratory tests of the improved material are encouraging, but again, the improvement has not been validated in the flight environment. 2 years of intensive work across multiple facilities and multiple technical disciplines have produced a substantially improved understanding of what happened and why. They have produced updated models, improved materials, modified trajectory designs, and a more complete picture of the failure mechanism. They have not produced certainty. The program is preparing to fly a crewed mission based on an improved understanding of a problem that was not understood when the problem was first encountered using an improved material whose improvement is validated by laboratory tests but not by flight, on a modified trajectory whose thermal environment has been analyzed but not tested in the one way that ultimately matters, an actual flight. Chapter 6. The specific risk. What happens if it fails on Artemis II? Before going further, it is important to be precise about what the risk actually is. Not in the abstract sense of the heat shield could fail, but in the specific, physical, detailed sense of what failure would look like and what its consequences would be. The AVCOAT heat shield protects the crew module through ablation. The ablation removes material, and in doing so removes the thermal energy that would otherwise heat the capsule to lethal temperatures. The heat shield is designed with a specific thickness that, based on the thermal models, provides sufficient ablative material to last through the re-entry with an acceptable margin. If the ablation rate were higher than predicted, if more material were removed per unit of heating than the models predict, the heat shield could be ablated through before re-entry was complete, exposing the underlying structure to the thermal environment. The anomalous char ejection observed on Artemis I is an accelerated form of material loss. When the char layer cracks and pieces eject from the surface, the material removal rate is higher than the smooth, progressive ablation that the models were designed for. The underlying material, fresh AVCOAT, is then exposed to the thermal environment earlier and at a higher temperature than it would have been in the smooth ablation case. On Artemis I, the char ejection was apparently not severe enough to exhaust the heat shield. There was sufficient remaining thickness that even with the anomalous material loss, the heat shield provided adequate protection through the end of re-entry. The thermal protection was maintained. The capsule survived. But the Artemis I re-entry was an uncrewed mission. An uncrewed Orion is slightly lighter than a crewed Orion because it does not carry the full life support consumables, the crew-specific equipment, and the 4 crew members themselves. A heavier capsule re-enters with slightly different dynamics, a slightly different trim condition, a slightly different angle of attack, a slightly different heating distribution across the heat shield. The differences are not enormous, but they are not zero. Additionally, the Artemis I mission was flown on a trajectory specifically designed for the test flight. The exact trajectory was chosen partly for technical reasons and partly for operational convenience. Artemis II will be flown on a trajectory designed for the crewed mission's specific objectives, which may differ in details that affect the re-entry heating profile. Perhaps most importantly, Artemis III and subsequent missions will return from the Moon at higher velocities than Artemis I and Artemis II. Because they will carry heavier payloads, the crew plus the full complement of equipment for surface operations, and will be returning from direct lunar landing missions rather than the more modest flyby of Artemis II. Higher return velocity means higher kinetic energy, means higher heating rates on re-entry. The heat shield that experienced anomalous behavior on Artemis I was flying at the minimum re-entry velocity for a lunar return mission. Future missions will be flying at higher velocities. The question the engineers must answer is not, did the heat shield survive Artemis I? It did. The question is, do we understand the failure mode well enough to be confident that the heat shield will survive Artemis II and Artemis III and all subsequent missions at the design velocities? And the honest answer to that question, as of the most recent public information available, is not with the certainty that a program manager or a crew member should ideally have before flying. This is not a statement that Artemis II will fail. Most aircraft accidents do not happen on the second flight of a new type. The probability that the Artemis II heat shield will fail catastrophically is not high. The engineering team has done substantial work to understand and mitigate the risk. The material has been improved, the trajectory is being modified, but probability is not certainty. And in a crewed spaceflight program, the difference between probably fine and definitely fine is the difference between acceptable risk management and inadequate risk management. The specific failure scenario looks like this. During the skip phase of re-entry, the char layer that formed during the first atmospheric dip cools and experiences thermal stress that causes cracking and char ejection, as it did on Artemis I. If the char ejection is more severe than on Artemis I, due to higher re-entry velocity, slightly different heating distribution, or material properties in the specific heat shield regions affected, the char ejection exposes fresh avcoat to the second heating pulse before that avcoat has had time to develop a protective char. The exposed fresh avcoat ablates more rapidly than modeled, depleting the heat shield thickness faster than the margin allows. In the worst case, the heat shield is ablated through before re-entry is complete, and the thermal protection fails. If the thermal protection fails, if the plasma environment reaches the crew module structure, the aluminium-lithium alloy of the capsule's primary structure begins to melt and burn. The electrical systems fail. The structural integrity of the capsule fails. The crew does not survive. This is the failure scenario. It is not a likely scenario, but it is a possible scenario. To understand why the program considers the risk manageable, while critics consider it inadequately characterized, it helps to understand how spacecraft heat shield margins are expressed. A heat shield margin is typically expressed as a ratio. The thickness of heat shield material available divided by the thickness of material predicted to be consumed during re-entry. A margin of 1.5 means the heat shield has 50% more material than the models predict will be consumed, a 50% safety buffer. A margin of 1.0 means the heat shield has exactly as much material as the models predict will be consumed, no buffer at all. The Orion heat shield was designed with margins that the program considers adequate. The specific numbers are not publicly disclosed in full detail, but the general principle is that aerospace heat shields are designed with substantial margins large enough to accommodate the uncertainty in the thermal environment model, the uncertainty in the material properties, and the uncertainty in the manufacturing quality. The question that the Artemis I anomaly raises is, are those margins still adequate when the failure mode is one that was not included in the margin calculation? The margins were calculated against the thermal environment as the models described it, and against the ablation behavior as the models predicted it. A failure mode that was not in the models, anomalous char ejection driven by two-phase heating, is not a failure mode that the margins were calculated to accommodate. The margins may or may not be sufficient. Without knowing the severity of the anomalous behavior as a function of the specific thermal environment, and without having a validated model of that behavior, you cannot calculate whether the margins hold. This is the core of the engineering uncertainty. Not will the heat shield survive, in the binary sense, it probably will, but do we know by how much it will survive? And do we know whether the conditions on Artemis II are within the regime where our updated models are reliable? The honest answer is not completely. And its possibility is what has kept Artemis II on the EU ground while engineers work through the problem. Chapter 7: The political pressure and the decision to fly? The heat shield investigation is not happening in a vacuum. It is happening inside one of the most politically contentious and budget-constrained government programs in recent memory, on a timeline that has already slipped by years, and that is under pressure from both internal and external forces to stop slipping. The Artemis program is expensive. The Space Launch System costs approximately $4.1 billion per launch. The Orion spacecraft has cost approximately $20 billion to develop. The total Artemis program cost, through the first crewed lunar landing, is estimated by the NASA Inspector General at approximately $93 billion. These numbers are difficult to defend in a political environment where NASA's annual budget is approximately $24 billion, and where every year the program does not fly is another year during which that budget is being spent with no crewed mission to show for it. The political pressure to fly is real and documented. Multiple congressional hearings have featured testimony from members pressing NASA administrators and program managers for specific, firm launch dates. NASA's Artemis program has been subject to an unusual level of congressional scrutiny precisely because of its history of schedule slippage and cost growth, and because several members of Congress, including members of committees with jurisdiction over NASA's budget, have publicly questioned whether the program is being managed effectively. The competition with China adds another layer of pressure. The Chinese crewed lunar program is publicly targeting 2030 for its first taikonaut landing on the moon. The American program is targeting the mid-2020s to late 2020s for a crewed lunar landing. If Artemis II slips further and Artemis III slips in consequence, the American lead over China in this renewed space race could narrow to the point where the outcome is genuinely uncertain. This is not just a matter of national prestige, though prestige matters, but of strategic positioning in the cislunar environment, including the water ice resources at the lunar South Pole that will be essential for any sustained lunar presence. The pressure to fly is therefore not simply bureaucratic impatience. There are legitimate reasons why the program needs to move forward, why delay has costs, and why NASA leadership is under genuine and justifiable pressure to demonstrate that the program can execute. But pressure to fly is precisely the condition that produced both Challenger and Columbia. In both cases, the decision to launch or re-enter was made under schedule pressure. Pressure not to delay further. Pressure not to let the program fall behind. Pressure not to disappoint stakeholders who were expecting the mission to proceed. In both cases, the technical concerns that should have grounded the vehicle were treated as manageable risks rather than as mission-critical unknowns. In both cases, the pressure to fly contributed to a decision-making environment in which the threshold for flying was lower than it should have been. The NASA Inspector General's report on the Artemis II heat shield drew this parallel explicitly. Not to suggest that Artemis II will fail, the report is careful not to claim that, but to identify the structural conditions that historically precede catastrophic failure in crewed spaceflight programs, and to note that those structural conditions are present in the Artemis II situation. The structural conditions are a technical anomaly not fully understood, a pressure to fly despite incomplete understanding, and a pattern of communication that minimizes the apparent severity of the anomaly in ways that do not fully inform external stakeholders. The former NASA astronaut and safety advocate Scott Parazynski, in testimony to congressional committees, characterized the situation in terms that many in the aerospace safety community found accurate. The program is in a situation where the known unknowns, the things we know we don't know about the heat shield behavior, are significant, and where the unknown unknowns, the things we don't know, the failure modes that didn't appear in the one flight we've done and haven't appeared in the limited arc jet testing, could be more dangerous than the known unknowns. NASA's current public position is that Artemis II will not fly until the mission management team and the Flight Readiness Review boards are satisfied that the risk to the crew is within acceptable bounds. The agency has stated that the heat shield investigation has made substantial progress and that specific mitigations, the trajectory modifications, the improved AVCOAT material, the updated models, provide adequate confidence for the crewed mission to proceed. A formal flight readiness review process, including independent review boards, will make the final determination. What the agency has not publicly provided, and what critics argue it should, is a detailed quantitative account of the residual risk. What is the probability of heat shield failure on Artemis II? And what is the probability that the failure would be catastrophic? These numbers exist in some form in the program's risk database. They have not been made publicly available in the form that would allow external stakeholders to independently assess whether the risk is actually within acceptable bounds, or whether acceptable is being defined in a way that is influenced by the pressure to fly. Chapter 8. The 4 people getting into the capsule? None of the above. The anomaly, the investigation, the political pressure, the residual uncertainty, changes one fundamental fact about this story. 4 specific human beings are going to get into this spacecraft. They are going to fly to the moon, and they are going to come back through the atmosphere on this heat shield. They know. Let that sink in for a moment. The crew of Artemis II has been briefed on the heat shield anomaly. They have attended the technical reviews. They have sat with the engineers who investigated the failure and the engineers who designed the mitigations. They have asked the hard questions that experienced test pilots and mission specialists ask when their lives depend on understanding what the machine they are about to fly has done and what it might do. Reed Wiseman, the mission commander, is a U.S. Navy test pilot. His career has been built on flying aircraft and spacecraft at the edge of their operational envelope and reporting back with precision on what they do and what they don't do. He understands risk management at a technical level that most people who write and talk about risk do not. He has evaluated the heat shield situation with the same analytical framework he would use to evaluate any other risk on any other test mission. And he has decided with full information that the mission is worth flying. Victor Glover, the pilot, will be the first Black astronaut to fly beyond low Earth orbit. The historical significance of his flight is immense. He also understands exactly what the heat shield showed on its first flight. He has been a part of the technical community working through this problem, and he has concluded that the risk, as currently characterized and mitigated, is acceptable. Christina Koch, who will be the first woman to travel to the moon, holds the record for the longest single spaceflight by a woman. She has spent time in environments where the consequences of equipment failure are fatal and where there is no immediate rescue. She has cultivated the kind of risk literacy that comes from actually working in dangerous environments, not just calculating probabilities. She is going. Jeremy Hansen, the Canadian Space Agency astronaut, who will become the first non-American to fly beyond low Earth orbit, is on his first spaceflight. He will be in that capsule for his maiden voyage, not to low Earth orbit, but to the moon, on a spacecraft with a heat shield, whose behavior under the reentry conditions it will face is imperfectly understood. These 4 people have made informed choices. They deserve to have that choice respected for what it is. A decision made by highly trained professionals who understand the risk better than most people can, who have weighed the mission's importance against the risk, and who have concluded that the mission should fly. At the same time, their willingness to accept the risk does not settle the question of whether the risk management is adequate. Crew acceptance of risk is a necessary condition for flying a crewed mission with known residual risks. It is not a sufficient condition. The program's responsibility is not only to inform the crew of the risks and get their consent. It is to reduce the risks to the lowest level that is technically achievable, to communicate those risks honestly to all stakeholders, and to ensure that the decision to fly is made by people who have the full picture, not a picture shaped by institutional pressure to minimize the apparent severity of anomalies that remain incompletely understood. The heat shield cracked on the first flight. The crack was not catastrophic, but it was real, and it was not supposed to happen, and it was not in the models, and the models that have now been updated have not been verified in flight. The 4 people getting into Orion know this. The question is whether everyone else in the chain of command that will make the final call to fly, and everyone in the American public who funds this program, knows it too. Chapter 9. The technical fixes. What NASA has actually done it is worth being precise about what the program has actually done in response to the heat shield anomaly, because the public picture of NASA is fixing the problem is somewhat misleading. The program is not fixing the heat shield in the sense of redesigning it or replacing the problematic material with something demonstrably better. The program is implementing a set of mitigations that are intended to reduce the likelihood and severity of the anomalous char behavior on Artemis II. These are meaningfully different things. The first and most significant mitigation is the trajectory modification. The Artemis II re-entry trajectory is being modified to reduce the peak aerothermal heating during the first atmospheric dip of the skip re-entry. By shallowing the entry angle slightly, entering the atmosphere at a slightly less steep angle than Artemis I, the spacecraft spends more time in the upper, thinner part of the atmosphere during the first dip, which reduces the peak heating rate. A lower peak heating rate during the first dip means a less intensively charred heat shield surface at the end of the first dip, which means a less highly stressed char layer during the cooling of the skip phase, which means, in theory, less susceptibility to the cracking and ejection that occurred on Artemis I. The trajectory modification has been validated analytically using the updated thermal models. It has been validated experimentally using the arc jet tests, which were conducted at the lower heating rates that the modified trajectory would produce, and showed less severe char behavior. What it has not been validated against is an actual flight at the modified trajectory with the actual Orion heat shield in the actual flight environment. The second mitigation is the improvement to the avcoat material itself. The Orion 004 heat shield, the one that will fly on Artemis II, was manufactured with process improvements focused on reducing the variability in the avcoat microstructure. Specifically, the manufacturing process was modified to reduce the void content in the applied avcoat. Voids being small pockets of air or gas trapped within the material during application that can act as initiation sites for cracking. The improved material also shows more uniform density and thermal properties across the heat shield surface. The rationale for this improvement is straightforward. If the char layer is more mechanically uniform, it should be more resistant to the stress-driven cracking that caused the anomalous ejection. A char layer with fewer initiation sites for cracking, forming from a more uniform base material, should crack less readily under the same thermal stress loading. The material improvement has been characterized in laboratory testing and in arc jet testing of samples from the Artemis II heat shield material. The test results show that the improved material produces a more uniform char layer and shows less tendency toward catastrophic cracking under the two-phase heating profiles tested. This is encouraging. It is not, in engineering terms, a qualification. Qualification requires testing under flight representative conditions that the arc jet tests can only approximate, and it normally requires demonstrating that the material performs within specification across the full range of the intended operating environment, not just at the specific conditions that were tested. The third mitigation is the updated monitoring and analysis framework. The program has developed more detailed instrumentation and data analysis procedures for the Artemis II heat shield that will allow the post-flight inspection to be conducted more quickly and to a higher level of detail than the Artemis I inspection. If the anomalous char behavior recurs on Artemis II, the program will know more quickly and in more detail what happened. This mitigation is important for the program's learning trajectory. But from the perspective of the Artemis II crew, it is not a safety mitigation. It helps the program understand what happened after the crew has already returned or not returned. The improved post-flight analysis framework does not change what happens to the crew during re-entry. If the heat shield fails during Artemis II, faster and better post-flight analysis of the wreckage will tell engineers why it failed, which is valuable for future missions, but provides no protection for the crew on this one. The fourth element, less a mitigation than a constraint, is the limitation of the Artemis II mission profile to conditions that are within the validated regime of the updated models. The Artemis II re-entry velocity will be essentially the same as Artemis I. The mission is a lunar flyby, not a lunar landing, and the return velocity from a flyby is similar to the return velocity from the Artemis I trajectory. This means the heat shield will face a thermal environment similar to, though not identical to, the environment it experienced on Artemis I. The updated models and the trajectory modification are intended to produce a less severe instance of that thermal environment. The ArcJet testing program deserves more detailed examination because it is the primary experimental basis for the program's confidence in its mitigations. And its limitations are real and significant. An ArcJet is a facility that uses electrical power to heat a gas stream to plasma temperatures, creating a flow of ionized gas that can be directed at a test article, a piece of heat shield material, or a heat shield segment, to simulate the aerothermal environment of re-entry. The NASA Ames Research Center operates several ArcJet facilities with different power levels, nozzle configurations, and flow conditions. The largest of these can replicate some aspects of the aerothermal environment of lunar return re-entries. The fundamental limitation of ArcJet testing is that it cannot perfectly replicate the actual re-entry environment. The actual re-entry environment is characterized by a specific combination of pressure, temperature, velocity, gas composition, and duration that the ArcJet facilities can approach but cannot exactly match. The scale is different. A full-scale Orion heat shield is 5 meters in diameter, and no ArcJet facility can test a sample at anything close to that scale under flight representative conditions. The flow chemistry is different. The actual re-entry plasma has a specific composition that the ArcJet plasma can approximate but not duplicate. The duration is different. A real re-entry lasts 10 to 15 minutes, while most ArcJet tests are conducted on much shorter timescales. These are not minor differences. The behavior of ablative heat shield materials under aerothermal loading is sensitive to the specific conditions. Scale effects, chemistry effects, and duration effects are all real and significant in the physics of char formation and ablation. The ArcJet tests provide valuable data, but they are fundamentally surrogate tests, not replication tests. They tell you how the material behaves under conditions that approximate but do not replicate the flight environment. The gap between approximately and exactly is where engineering uncertainty lives. The program's engineers understand this. They have used the ArcJet data in the context of established test analysis correlation methods that explicitly account for the known differences between ArcJet and flight conditions, and that use those corrections to extrapolate from the test data to the flight prediction. These methods are the standard tools of thermal protection system development, and they are well developed, but they rest on physical models of the heat transfer and material response that, as the Artemis I anomaly demonstrated, can be incomplete. What the program has not done, and what critics argue it should, is fly another uncrewed mission at the Artemis II trajectory before committing the crew. An additional uncrewed test flight at the modified trajectory with the improved heat shield material would generate one more data point validating the mitigations in the actual flight environment. This option has been discussed within the program. It has been weighed against the cost, another SLS and Orion, approximately $4 billion, and the schedule impact, additional years of delay, and against the fact that Artemis I, the one uncrewed test flight that has been flown, is itself the source of the anomaly that created the problem in the first place. An additional uncrewed test flight would be valuable, but is not being planned. The decision not to fly an additional uncrewed test is defensible on engineering and programmatic grounds. The mitigations that have been implemented represent a genuine improvement over the Artemis I configuration. The trajectory modification and material improvement are not trivial changes. They are substantive engineering responses to the identified mechanism. The analytical and experimental evidence supporting these mitigations is substantial. The residual uncertainty is real, but is the kind of uncertainty that exists in every crewed spaceflight program at some level, but defensible on engineering and programmatic grounds, and appropriate given the available evidence, are not the same judgment. Reasonable engineers can look at the same evidence and reach different conclusions about whether the mitigations are sufficient to justify flying with crew. The history of crewed spaceflight has more examples of engineers who concluded that the risk was acceptable but were wrong than it has examples of engineers who concluded that the risk was unacceptable but were wrong. Being too conservative costs money and schedule. Being too liberal costs lives. Chapter 10. What a heat shield failure during crewed re-entry would actually mean. The language of probability and risk margins is useful for engineering calculations, but it can create a certain psychological distance from what the numbers actually describe. Let's remove that distance. If the Orion heat shield fails during crewed re-entry, if the anomalous char ejection on Artemis II is more severe than on Artemis I, more severe than the updated models and trajectory modification can contain, the physical sequence of events that follows is specific and irreversible. The first indication would likely be a rise in the temperature readings from the sensors embedded in the heat shield structure. Orion has temperature sensors at multiple depths through the heat shield, allowing engineers in mission control to monitor the thermal state of the shield in real time during re-entry. In a normal re-entry, these temperatures rise at predicted rates and remain within the predicted bands. If the thermal protection is failing, if more heat is penetrating the shield than expected, the deeper sensors would begin to read higher temperatures than predicted, and the rate of temperature rise would be higher than the models predicted. The crew and mission controllers would be aware that something was wrong. The sensor data would tell them so, but there would be nothing they could do about it. Re-entry is committed. At 39,000 kilometers per hour in the upper atmosphere, there is no trajectory maneuver available that improves the situation. There is no way to reduce the heating by flying differently. The only way out is through. The crew must wait for the re-entry to complete, and if the heat shield fails before it completes, the wait ends badly. The specific failure mode in the heat shield is thermal breakthrough, the penetration of the plasma heating environment through the heat shield to the underlying capsule structure. The Orion crew module's primary structure is an aluminium-lithium alloy. Aluminium melts at approximately 660 degrees Celsius. The plasma environment outside the heat shield is at approximately 2,760 degrees Celsius at the stagnation point. If the heat shield is breached, if the plasma heating reaches the aluminium structure, the aluminium begins to burn and melt within seconds. The capsule does not have the structural integrity to maintain its shape or protect its interior under these conditions. The penetration of the structural wall would allow plasma to enter the crew compartment. The crew compartment at this point in re-entry is pressurized with a nitrogen-oxygen atmosphere at approximately sea level equivalent pressure. The introduction of plasma at several thousand degrees into a pressurized compartment is catastrophic. The crew would have no warning that was not simultaneously a death notice. This description is not meant to be gratuitous or sensational. It is meant to be honest about what the probability numbers in the engineering risk assessments actually describe. When an engineer writes, probability of crew loss of mission equals X%, the physical content of that X% is the scenario described above. Treating it as an abstract number is a way of not thinking about it fully. Thinking about it fully is what the people who make go/no-go decisions are supposed to do. The crew of Artemis II would experience the re-entry as follows. They are strapped into their seats in their launch and re-entry pressure suits, with the capsule-oriented heat shield forward, decelerating from orbital velocity. The G-loading would be increasing, building to several times the force of gravity as the atmosphere decelerates the capsule. The view through the windows would show the characteristic orange and pink glow of the plasma sheath forming around the capsule. The radio would be in blackout. The plasma sheath blocks radio communication during the most intense part of re-entry, a blackout that typically lasts several minutes. During this blackout, the crew is out of contact with mission control. Mission controllers can see some telemetry through the plasma, but voice communication is not possible. In the event of a heat shield failure, the crew would have access to the temperature sensor, data that mission controllers also see. They might be aware from the anomalous sensor readings that the heat shield was not performing nominally. They would not be able to communicate this to the ground. They would not be able to take any corrective action. They would be in the most extreme environment any human being has ever entered, in a vehicle that was losing its ability to protect them, unable to communicate, and with the entire transit history of 11 days behind them. The launch, the 3-day journey to the moon, the lunar flyby, the 3-day return, serving as context for the last few minutes. The crew of Artemis II knows this is a possibility, not a probability, a possibility, and they are getting in the capsule anyway. Chapter 11. The broader questions. What this says about how we fly. The heat shield anomaly on Artemis I is, in one sense, a specific technical problem with a specific spacecraft system. In another sense, it is a window into something more fundamental about how crewed spaceflight programs work and how they fail. Crewed spaceflight has always involved accepting risks that, if articulated clearly to the general public, would prompt serious questions about whether the missions should proceed. The Mercury, Gemini, and Apollo programs flew with risk levels that, by modern standards, would be considered unacceptably high. John Glenn's first orbital flight was conducted with full knowledge that the retro rocket package on his Mercury capsule had sent a signal indicating the heat shield might be loose. A signal that turned out to be a faulty sensor, but that was not known to be faulty until after the mission. The Apollo 1 crew died in a spacecraft that had known design deficiencies. The pure oxygen atmosphere at higher than sea level pressure, the use of flammable materials in the cabin, that engineers within the program had raised concerns about before the fatal fire. The history of spaceflight is not a history of programs that never accepted uncertain risk. It is a history of programs that accepted uncertain risk, sometimes successfully and sometimes catastrophically, and that learned, or failed to learn, from each experience. The lessons of Challenger and Columbia, the institutional lessons about how safety concerns are communicated, about how schedule pressure affects technical decision-making, about how the definition of acceptable risk can drift in an environment of sustained pressure to fly, have been repeatedly articulated, codified in NASA safety culture documents, incorporated into training programs, and then, in various ways, gradually eroded by the same institutional dynamics that produced the original failures. The heat shield anomaly on Artemis, one does not fit the Challenger or Columbia pattern in a simple way. It is not a situation in which engineers clearly identified a risk of imminent catastrophic failure and were overruled by management. The engineers are genuinely uncertain about the severity of the risk. The investigation has been substantive and serious. The mitigations are technically credible. The flight readiness review process, if it is conducted with full information and genuine independence, is the appropriate mechanism for making the go/no-go decision. What it does fit is the earlier part of the Challenger and Columbia pattern, a situation in which a technical anomaly revealed a gap in the models, in which the program characterized that gap in ways that minimized its apparent severity in external communications, and in which the program is under significant schedule and budget pressure while working to resolve the gap. The lesson of Challenger and Columbia is not that NASA flew knowing the vehicles would fail. The lesson is that the institutional conditions that lead to flying with incompletely understood risks are specific, recognizable, and have occurred multiple times in the program's history. The conditions are present here. The question of what acceptable risk means for crewed spaceflight is one that the U.S. Congress, NASA, and the public have never fully resolved. NASA uses a probabilistic risk assessment framework in which the risk of crew loss per mission is characterized as a specific number, typically in the range of 1 in 100 to 1 in 300, for crewed missions at the current level of program maturity. The Artemis program's public statements have not provided a specific probability of crew loss associated with the heat shield residual risk. But the residual uncertainty in the updated models means that any probability estimate for this specific risk has a wide uncertainty range. There is a fundamental tension in crewed spaceflight between two incompatible imperatives. The first imperative is to advance human exploration and to use the knowledge gained to build towards the future. This imperative demands accepting risk, because exploration inherently involves risk, and refusing to accept any risk means never going anywhere. The second imperative is to protect human life, not because human life is more valuable than exploration, but because the loss of a crew is both a human tragedy and a programmatic catastrophe that sets back the exploration imperative for years or decades. Challenger grounded the Space Shuttle program for 32 months. Columbia grounded it for 29 months. A loss of the Artemis II crew would ground the program for years, almost certainly kill the Artemis program as currently constituted, and potentially end American crewed spaceflight at the very moment when the space race with China is reaching its most competitive phase. The best way to advance the exploration imperative in a program with limited budget and limited political durability is not to fly with incompletely understood risks and hope that the margins are sufficient. The best way is to understand the risks fully, to mitigate them to the extent that is technically achievable, to communicate them honestly, and to make go/no-go decisions in an environment that is genuinely free from the pressure to fly that has preceded every major crewed spaceflight accident. Whether the current Artemis II program meets those standards is a question that the people inside the program, the independent review boards, the Inspector General, and ultimately NASA's leadership are responsible for answering. The heat shield cracked, not a metaphor. The material failed in a way that was not supposed to happen. And the question that comes from that crack is not just, is it fixed? But how do we make sure we know what we don't know before we put people inside? Chapter 12. The decision to fly. Who makes it and how? The decision to launch Artemis II will not be made by one person. It will be made through a formal, multi-stage review process that is NASA's standard mechanism for certifying crewed missions as ready to fly. Understanding this process and understanding its limitations is essential for evaluating whether the heat shield anomaly is being handled appropriately. The first stage of the process is the mission management team's ongoing assessment. The MMT has been tracking the heat shield investigation since the anomaly was confirmed in early 2023. It has been receiving regular briefings on the investigation's progress, the updated models, the ArcJet test results, and the material improvements. The MMT's role is to maintain a current assessment of the program's readiness and to escalate concerns to higher review levels when warranted. The second stage is the Flight Readiness Review, or FRR. The FRR is a formal board review that brings together the technical leadership of the program, the chief engineers, the program manager, the astronaut office, the safety office, along with independent reviewers from other NASA programs and centers. The FRR is the formal technical gate that must be passed before a crewed mission can proceed to launch. Each major system on the spacecraft must be certified as ready, and any open items, technical issues that have not been fully resolved must be dispositioned. Either closed, the issue is resolved; accepted, the issue is accepted as a known and characterized risk within the program's risk tolerance; or elevated, the issue is considered a potential mission stopper requiring further action. The heat shield anomaly will be brought to the FRR as an open item. The program's technical case for disposition, for accepting the residual risk as within tolerance, will be based on the updated models, the trajectory modifications, the material improvements, and the arc jet test data. The FRR board will review this case, ask questions, and either accept the disposition or require further action. The third stage is the launch readiness review, conducted closer to the launch date, which confirms that the specific hardware, the specific Orion 004 crew module, the specific SLS core stage, the specific solid rocket boosters, is ready in its as-built, as-inspected condition to fly the mission. By this point, the heat shield anomaly is expected to have been formally closed at the FRR level. The process is thorough. It was designed specifically to avoid the institutional failures that produced Challenger and Columbia. It involves independent reviewers. It has a formal structure for elevating concerns. It explicitly requires that open technical items be dispositioned before the flight is certified. But the process has limitations. The most important limitation is that the FRR process is ultimately about accepting or rejecting a technical case made by the program itself. The program's engineers develop the case, and independent reviewers evaluate it. But the independent reviewers are reviewing the program's case. They are not conducting an independent investigation. Their ability to challenge the case is limited by their access to the underlying data and by the time available for the review. If the program's case is based on updated models and test data that have not been independently replicated and that rest on physical assumptions that are not fully validated, the FRR process may not be able to identify that limitation. There is also the question of what within tolerance means. The program has a risk tolerance standard, a maximum acceptable probability of crew loss per mission, and the formal process requires that the risk assessment show the mission meets that standard. But the risk assessment for the heat shield anomaly depends on models that the anomaly itself demonstrated to be incomplete. The residual uncertainty in those models means that the probability estimate for heat shield failure has a wide uncertainty range, and the formal risk assessment may not fully capture how wide that range is. A risk assessment that shows a central estimate within tolerance with an uncertainty range that extends outside tolerance is different from a risk assessment that shows a central estimate within tolerance with narrow uncertainty. The difference matters for the go/no-go decision, and the FRR process may or may not surface this distinction clearly. The most important safeguard in the process, the one that provides the greatest real-world protection against the institutional pressures that have preceded past accidents, is the independence and the authority of the review boards. The FRR boards have the authority to require additional testing, to hold the launch, or to declare the mission not ready. Whether they will exercise that authority in the face of program management's recommendation to proceed in an environment of significant schedule and budget pressure is ultimately a question about the culture of the organization and the character of the individuals involved. That is not something that can be evaluated from outside the process. What the NASA Inspector General recommended and what independent safety advocates have endorsed. It is worth being specific about what the independent oversight community has actually said, because the public discourse sometimes conflates different levels of concern. The NASA Inspector General's November 2023 report was a detailed, technically informed document that raised specific concerns about specific aspects of the program's risk management. It did not say the heat shield would fail. It did not recommend grounding the program. It recommended greater transparency and specifically called for NASA to provide a more complete account of the residual risks to external stakeholders before flying the crewed mission. The Aerospace Safety Advisory Panel, the external committee that has advised NASA on safety matters since the Apollo 1 fire, has been monitoring the heat shield investigation. Its annual reports during the investigation period have noted the anomaly, noted the program's investigation efforts, and noted the importance of ensuring that the investigation is complete before committing the crew. The panel's assessments have been characterized as expressing cautious confidence in the program's approach, neither endorsing unconditional go nor recommending hold. This is the kind of qualified assessment that reflects genuine uncertainty. The investigation has been substantive, the mitigations are credible, but the residual risk has not been fully characterized. The Aerospace Safety Advisory Panel's role is advisory, not decision-making. Its assessments are provided to the NASA administrator and to Congress, but the program is not required to follow them. The panel cannot halt a mission. It can only recommend. The independent oversight community has not spoken with a unified voice, demanding that Artemis II be grounded. What it has said, consistently, is that the residual risk needs to be more clearly characterized and more transparently communicated before the crewed mission flies. Whether that characterization and communication have occurred to the required level is the question that the FRR process is supposed to answer, and that external observers cannot fully evaluate without the data that the program has not made public. What the NASA Inspector General recommended, and what independent safety advocates have endorsed, is that the program provide full transparency about the residual risk assessment. Not just the central estimate, but the uncertainty range, the assumptions underlying it, and the degree to which the updated models are validated versus extrapolated. This transparency would allow external stakeholders, the members of Congress who fund the program, the safety community, and the public, to make their own assessment of whether the risk is acceptable. Without this transparency, the external assessment of the program's risk management must rely on the program's own characterization of its work, which, as the IG documented, has not always been adequate. Chapter 13. The View from Inside. What the astronauts know that we don't. There is an aspect of this story that outside observers, including this video, cannot fully access. The internal technical briefings that the Artemis II crew has received on the heat shield anomaly, and the crew's own technical assessment of the risk. Astronauts assigned to specific missions are deeply integrated into the technical program for that mission. They attend engineering reviews, design reviews, and test reviews. They participate in simulations and training runs that are designed to prepare them for nominal and off-nominal situations. They ask questions that the test pilot in them demands answers to. They get those answers, or they push back when the answers are inadequate. The 4 crew members of Artemis II have been in the room for the heat shield reviews. They have seen the post-flight data from Artemis I. They have heard the technical case for the mitigations. They have been in the ArcJet test facilities. They have handled samples of the AVCOAT material. They have sat with the engineers who modeled the failure mechanism and with the engineers who designed the trajectory modification and with the engineers who qualified the improved material. Their assessment, the assessment of 4 highly trained, technically literate professionals who have access to information that no outside observer has access to, is that the mission is worth flying. It is worth understanding what goes into that assessment, not just the engineering homework, but the specific cognitive and cultural environment in which test pilots and astronauts evaluate risk. The culture of the astronaut corps, and more broadly the culture of military and experimental flight test, trains people to engage with risk in a specific way that is different from the general population's approach to risk. Test pilots learn through their training and through their careers to identify the specific parameters of an envelope, the known limits of a system's safe operating range, and to evaluate where a given test point sits relative to that envelope. They learn to distinguish between unknown and potentially catastrophic, and unknown but bounded risks. They learn to evaluate whether the unknowns are material unknowns, ones that could change the outcome, or immaterial unknowns, ones that are present but don't affect the fundamental risk picture. And they learn to accept the material unknowns that are inherent to flying a new system for the first time, because if you wait until all material unknowns are resolved, you never fly anything new. This cognitive framework is valuable and appropriate for test flying. It produces people who can make rational, informed decisions about risk in the presence of uncertainty, which is exactly what you need for a test pilot, but it is also a framework that, applied in an institutional environment with schedule and budget pressure, can be pushed in the direction of accepting larger unknowns as bounded or immaterial than they actually are. The institutional environment shapes what kinds of unknowns get classified as acceptable. The 4 Artemis II crew members have applied this framework to the heat shield situation. They have categorized the residual uncertainty as bounded and acceptable. Their categorization is based on their technical assessment of the engineering case, the updated models, the trajectory modification, the material improvement, the arc jet data. It is possible that their categorization is correct, and the heat shield will perform within the expected range. It is also possible that the unknown unknowns in the situation, the scale effects in the char formation, the trajectory variability, the uncharacterized failure modes, are more significant than the framework is able to identify from inside the program. This ambiguity does not diminish the crew's choice or their courage. It simply acknowledges the reality that even the best informed, most technically sophisticated risk assessment can be incomplete, and that the people inside the program are not the only people who should be evaluating whether the program's risk management is adequate. This is not a naive assessment. It is not an assessment driven by eagerness or bravado, or a failure to understand the risk. It is the assessment of people who have done the engineering homework and concluded, on the basis of that homework, that the program's mitigations are adequate. This matters. It matters enormously. And it also does not settle the question, for reasons that go beyond whether the crew's technical assessment is correct. Here is the thing that makes this genuinely hard. The people inside a program, the engineers, the crew, the program managers, are the best informed people about the program's specific technical situation. They have access to information that outside observers do not have. In that sense, their assessment of the risk should carry the most weight. At the same time, the people inside a program are not the best positioned people to assess whether the institutional dynamics of that program are producing appropriate risk management. The engineers who built the Challenger O-ring erosion data and who characterized it as an acceptable, known risk were technically sophisticated people who had access to the full dataset. They were also inside an institutional environment that, in ways they may not have fully recognized, was shaping their assessment of what acceptable meant. Roger Boisjoli, the Morton Thiokol engineer who famously opposed the Challenger launch, was also inside the program. He looked at the same data and reached a different conclusion about whether it was safe to fly. The institutional dynamics that independent oversight is designed to catch are not always visible from the inside. The feuilles, gradual normalization of anomalies, the process by which things that would have alarmed an outside observer become known and expected through repeated exposure, is a well-documented phenomenon in safety-critical systems research. The sociologist Diane Vaughan, in her definitive study of the Challenger disaster, described it as the normalization of deviance. The gradual process by which deviation from expected standards comes to be seen as normal and acceptable through repeated occurrence without catastrophic consequence. The heat shield anomaly on Artemis I was a deviation from the models. The models said it would ablate in one way, it ablated in another way. The deviation did not result in catastrophic failure. The program investigated it, developed an explanation, implemented mitigations, and is moving toward certifying the vehicle as ready to fly. This process is exactly what should happen. It is also exactly the kind of process through which, historically, deviations can be normalized in ways that are dangerous. The crew's willingness to fly, their informed, professional, technically grounded willingness, is a necessary condition for the mission to proceed. There is a specific way in which the normalization of deviance operates in technical programs that is worth making concrete, because it helps explain how intelligent, conscientious people can collectively arrive at risk assessments that, in retrospect, were insufficient. The process typically works like this. An anomaly is detected. Engineers investigate it. They develop an explanation, a physical mechanism, a failure mode, a root cause. They develop a mitigation. They test the mitigation. They present the case that the mitigation is adequate. At each stage, the engineers are doing what engineers do: gathering data, building models, testing hypotheses, and building a case. The case is built iteratively, and at each iteration, the engineers are comparing the new data to the emerging model and assessing whether the model is consistent with the data. The problem is that the model being developed is constrained by the existing understanding of the physical mechanisms. If the original anomaly revealed a physical mechanism that was not previously understood, which is precisely the case with the Artemis I heat shield, then the updated model is explaining something that was previously unexplained, using a mechanism that has been inferred rather than directly observed. The model may capture the essential physics. It may explain the anomaly correctly, but it may also be capturing a simplified version of the physics that works well in the regime that was tested and fails in a regime that was not tested. This is the specific form of unknown unknown that Scott Parazynski was describing when he characterized the heat shield situation. The known unknown is, we know that the two-phase heating produces anomalous char behavior, and we have uncertainty about how severe that behavior will be on Artemis II. The unknown unknown is, are there additional physical mechanisms at work? Mechanisms that did not manifest clearly enough in the Artemis I data or in the arc jet tests to be recognized, that could produce different or more severe failure modes under conditions slightly different from those already tested? One example of a potential unknown unknown in this context. The arc jet tests have been conducted with the AVCOAT material from the Artemis II heat shield, which is the improved material with reduced void content. But the arc jet tests are necessarily conducted on small coupons and segments, not on the full 5-meter heat shield. The full-scale heat shield has manufacturing characteristics, scale-dependent features of the AVCOAT application and cure process that the small coupons do not have. If there are scale-dependent effects in the char formation behavior that are not captured by the coupon-level tests, the program would not know about them until the actual heat shield flew. Another example. The trajectory modification is designed to reduce the peak heating during the first atmospheric dip. The modification has been validated analytically and in arc jet tests at the reduced heating rates. But the actual trajectory flown on Artemis II will depend on navigation performance, on the actual state of the atmosphere on re-entry day, on the specific trim and attitude of the capsule. There is inherent variability in the actual re-entry conditions that the program's trajectory analysis accounts for statistically, but that cannot be eliminated. The actual heating profile experienced by the heat shield on Artemis II will not be identical to the design trajectory. It will be some realization of the statistical distribution of possible trajectories around the design trajectory. The probability assessment depends on where in that distribution the actual trajectory falls. These are not arguments that the program's risk assessment is wrong. They are arguments that the uncertainty in the risk assessment is wider than the central estimate alone suggests, and that the width of the uncertainty is itself not fully known. It is not a sufficient validation that the program's risk management is adequate. Both things can be true simultaneously. The crew can be right that the mission is worth the risk, and the program can be insufficiently transparent about the full extent of the residual uncertainty. And in the event that the heat shield fails on Artemis II, the fact that the crew accepted the risk will not be comfort to anyone. Conclusion: the shield and what it represents. The Orion heat shield is 5 meters in diameter, bolted to the bottom of the crew module, filled with AVCOAT that burns away during re-entry to keep the people inside alive. It is the most critical single component on the spacecraft. It is the one system that has no backup, no redundancy, no contingency if it fails at the moment it is needed. It cracked on its first flight. Not through the entire material, not catastrophically, but in a way that was not supposed to happen, in a way that revealed a physical mechanism that was not in the models, in a way that consumed more of the safety margin than the program had accounted for, in a way that, had the conditions been slightly different, slightly higher velocity, slightly different trajectory, slightly more severe char ejection, might have been something worse. The program has worked for 2 years to understand what happened. It has updated the models. It has improved the material. It has modified the trajectory. It has conducted hundreds of hours of arc jet testing. The engineers who have done this work are talented, serious people who have genuinely tried to get this right. They have made the best case they can with the information available. And the information available is still ultimately one flight, one data point, one instance of the heat shield encountering the actual flight environment that can tell us what really happens, as opposed to what the models and the tests predict will happen. The 4 crew members of Artemis II have looked at all of this. They have sat with the uncertainty. They have asked the questions. They have received the answers. And they have chosen to go. There is something in that choice that is hard to fully articulate without either overstating its heroism or understating its weight. Going to the moon on a capsule that has never carried humans before, on a rocket that has never carried humans before, through a re-entry profile that produced an unexpected failure mode on its first flight. This is not a casual choice. It is not a choice made because the risk is known to be low and the people making it are comfortable with it. It is a choice made in full awareness of what the uncertainty means, what the worst case looks like, and what the mission is worth in the face of those considerations. That is the specific character of test piloting. That is the specific character of exploration at the frontier of the possible. It has always involved people choosing to get into machines that might kill them, because the knowledge and the capability on the other side of that choice is worth it. Alan Shepard flew a rocket that had exploded on its most recent unmanned test flight. Neil Armstrong flew a lunar module that had never been tested in the actual conditions of a lunar landing. The Artemis II crew is flying a capsule whose heat shield showed them something unexpected and whose full behavior under crude conditions is not completely characterized. This is the reality of where we are. The heat shield cracked. The engineers worked. The crew is going. The question of whether that is enough, whether the program has done what was technically achievable, communicated honestly, and protected the 4 people who trusted it with their lives, is a question that will be answered either before launch or after re-entry. We should hope it is answered before. The shield cracked on the first flight. Whether it holds on the second is the most important unanswered question in human spaceflight right now. And the answer depends not just on the avcoat material and the trajectory modification and the updated models, but on whether the people with the authority to say, "not yet," have been given the full picture and the institutional freedom to use it. The crew is ready to go. The question is whether we have done enough to make sure they come back. That question deserves to be asked by more than the engineers inside the program and the 4 crew members who have agreed to accept the risk. It deserves to be asked by the members of Congress who authorize the funding, by the journalists and scientists who cover this program, by the American public whose money built the spacecraft and whose name is on the mission. The heat shield crack is not a reason to cancel Artemis II. It is a reason to be honest about what the program knows and what it doesn't. The mitigations are credible. The investigation has been substantive. The crew is extraordinarily capable and fully informed. But probably safe is different from we know it's safe. And in the final analysis, the 4 people inside Orion during re-entry will be relying on the latter, while the program can only honestly provide the former. The Apollo program lost 3 crew members on the launch pad during a routine test. It lost them because of known design deficiencies that hadn't been fixed. In an environment of schedule pressure to beat the Soviets to the moon, the program paused, investigated, fixed what needed to be fixed, and then flew successfully 12 more times. The pause was painful and expensive. The alternative was unthinkable. Artemis II is not in the same position. The heat shield anomaly is not a known catastrophic deficiency. The mitigations are real improvements. The program has paused, investigated, and is implementing what it believes are adequate fixes. The FRR process will formally certify the readiness. The crew is ready to go. If the shield holds on re-entry, if the modified trajectory and improved material produce the less severe char behavior that the models and tests predict, then the Artemis II crew will splash down safely in the Pacific Ocean. The program will have a crewed mission to the vicinity of the moon under its belt for the first time since 1972. And the heat shield investigation will be regarded as a program management success. An anomaly detected, investigated, understood, and mitigated before it caused harm. If the shield does not hold, if the unknown unknowns turn out to be material, if the actual re-entry conditions fall in a regime where the updated models are insufficient, if the char ejection is more severe than the mitigations can contain, then the investigation will be reopened with data that was paid for at the highest possible price. The shield cracked on the first flight. The question of whether it holds on the second is being answered right now by engineers and program managers and review boards working through the hardest questions in crewed spaceflight. We should hope they get it right. We should demand the transparency to know whether they have. The crew is ready to go. The question is whether we have done enough to make sure they come back.